All right, let's dive right in. Welcome to this explainer where we're going to unpack a really fascinating contrast in the world of modern robotics. Because on one hand, you've got these flashy, perfectly choreographed public demonstrations that totally capture the world's imagination. But on the other hand, you have these completely invisible, wildly complex software pipelines that actually bring the machines to life. So today, we're going to connect those two worlds, moving straight from the blinding lights of a Las Vegas stage right down into the code that builds a virtual matrix for artificial intelligence.
We're starting our journey at the CES 2026 Tech Showcase, right inside a massive Las Vegas ballroom. Boston Dynamics dramatically dropped the curtain on their newest iteration of the humanoid robot, Atlas. The company's general manager for humanoid robots, Zachary Jakowski, announced to the crowd, "For the first time ever in public, please welcome Atlas to the stage." And this is actually a huge deal. It is incredibly rare for leading robot makers to publicly demonstrate their humanoids live. Why? Well, because fumbles attract a lot of unwanted attention. Actually, one of Russia's first humanoids recently practically fell on its face during a showcase. So startups usually stick to heavily edited social media videos where they can easily hide their mistakes. But Boston Dynamics, they took the risk live on stage.
To really appreciate this evolution, just think about the company's famous four-legged robot, Spot. To open the Hyundai event, a whole group of those Spot robots danced in perfect synchrony to a K-pop song. It's an incredible display, no doubt, but fundamentally, it is a quadruped. Now contrast that with the new Atlas prototype. This new, life-sized, bipedal machine literally picked itself up from the floor, walked fluidly around the stage, waved to the crowd, and even swiveled its head around like some sort of sci-fi owl. Now, to understand how Atlas reached this CES stage, we kind of have to look at Boston Dynamics' wild ownership history, because their corporate backing has shifted a lot over the decades they've been building robots in Massachusetts. Back in 2013, they were scooped up by Google. A few years later, they were sold off to the Japanese tech giant SoftBank. And finally, in 2021, the South Korean carmaker Hyundai acquired a controlling stake in the company. But here's the thing. That Hyundai ownership isn't just about funding cool science experiments. They are grounding this spectacle in absolute industrial reality. Right at the end of the demonstration, the robot gestured to a static, blue-colored product version of itself. And Hyundai announced that this specific version of Atlas is already in production. And get this, it will be deployed by the year 2028 to assemble cars at an electric vehicle manufacturing facility near Savannah, Georgia.
So that brings up the obvious question. How do you get a robot from a carefully controlled stage walk to a totally chaotic factory floor in just a couple of years? Well, you need immense intelligence. To hit that 2028 target, Hyundai announced a brand new partnership with Google's DeepMind. DeepMind is going to supply the highly advanced artificial intelligence required to make these Boston Dynamics robots truly autonomous. And in a really fascinating twist of corporate fate, this actually reconnects Boston Dynamics with Google, the very same parent company that bought them way back in 2013.
Which leads us to a crucial question for our explainer today. During that flawless CES demonstration, Atlas was actually being remotely piloted by an engineer standing just off stage. So, when we move past those remote piloted stage demos and aim for a 2028 factory deployment, how do these incredibly complex machines actually learn to navigate the chaos of our real world entirely on their own? The secret sauce here lies in a field called physical AI. This is the highly technical backstage discipline that makes all the front stage magic possible. Physical AI is all about building robots that can perceive, learn, and act in the completely unpredictable physical environments that you and I live in every single day. But here's the catch. You absolutely cannot just let a $1 million prototype blindly stumble around a laboratory to learn how to walk. It would destroy itself in under an hour. So to prevent these physical robots from constantly falling over, breaking, and costing their companies millions during that trial and error phase, developers use something else entirely. Enter environments like NVIDIA's Isaac ecosystem. And you can think of this quite literally as a virtual matrix where robots go to learn. By using advanced simulation, these robots can fail thousands and thousands of times in a digital world where hitting the reset button costs absolutely nothing. Let's break down exactly how this magic happens. Industry insiders call this the sim-to-real pipeline, and it comes down to 3 critical steps. Step 1, simulate the environment. Step 2, train the AI policy, which is essentially the robotic brain. And step 3, deploy that software back to the physical machine. Let's take a quick look at each step. Step 1 is simulation using a tool like Isaac Sim. This lets developers build a digital twin of the robot entirely from scratch.
But we're not just talking about a pretty 3D model here. It is a hardcore physics engine. They configure the exact physical properties, the weight, the joint friction, the center of balance. They even integrate virtual sensors so the digital robot sees the digital world exactly the way the physical machine will see the real world. It's perfectly mimicking reality.
Then we hit step 2, training with Isaac Lab. And the sheer scale here is mind-blowing. Developers use reinforcement learning, basically punishing the robot when it falls and rewarding it when it succeeds. But because it's all virtual, they can leverage massive GPU acceleration to train thousands of these digital robots simultaneously, in parallel. A physical robot would take days or weeks of clunky trial and error to learn a simple task. But in this virtual space, the AI figures out the right way to move in just a few hours.
Finally, we get to step 3, deployment. Using systems like Isaac ROS, you take those perfectly trained virtual policies, these robotic brains that have essentially spent lifetimes learning inside the simulation, and you drop them onto real physical hardware. But it is definitely not a simple copy-paste job. This involves integrating production-grade perception systems and incredibly strict real-time constraints, all to ensure that when the physical robot finally moves, it does so safely and predictably.
For a great example of how this software and hardware merge in the real world, just look at the Unitree G1 Humanoid. It's using NVIDIA's GR00T workflow, which is an end-to-end sim-first training policy designed to teach humanoids how to reach across tables and intuitively grasp everyday objects. And that software is then paired up with Jetson Thor, which provides the massive physical computing power needed right there on board the robot to process all of that complex AI in real time.
But what's really exciting is that this ecosystem scales way beyond giant car factories or flashy humanoid stage demos. This sim-to-real pipeline is actively democratizing robotics for everyone. You can use it for affordable open-source setups, like training a basic SO-101 robot arm with Hugging Face's Lee robot framework. You can use OpenUSD to build massive digital twins of entire multi-robot systems. It's even pushing into highly regulated fields through Isaac for healthcare, allowing developers to design safety-critical robots where precise domain adaptation is literally a matter of patient safety. So, as we step back and look at the whole picture, watching these incredible physical machines leave the CES stage, heading toward a real-world Hyundai factory by 2028, we have to consider the backstage software. With parallel GPU simulations compressing years of trial and error into mere hours, the speed of robotic evolution isn't waiting on physical hardware to stop breaking anymore. It's scaling at the speed of software. Which leaves us with one final, undeniable question. If they're learning this fast, how soon until we see them stepping out of the factories and right into our homes? Thank you for joining me on this explainer. I hope you found the journey from the stage to the simulation as fascinating as I did.